For years, loitering munitions flew low and slow, but the battlefield is accelerating. Attack drones are adopting turbojets, turning what used to be a propeller-driven nuisance into a high-speed strike weapon. Early attrition warfare relied on platforms like the Shahed 136, driven by simple, inexpensive piston engines. This chart illustrates the problem: speed regime. Legacy drones max out around 180 kilometers per hour. Jet-powered variants push that boundary to 600 kilometers per hour. To understand why this breaks manual air defense, look at the human OODA loop, the baseline time it takes an operator to observe, orient, decide, and act. At 600 kilometers per hour, the cognitive latency of processing radar data and manually aiming an interceptor is simply too long. The drone hits the target before a human can finish orienting. By adopting jet propulsion, attackers have mathematically closed the time window for human-in-the-loop defense to zero. The defense industry has responded with physical hardware engineered to match these kinematics. Systems like the Anduril Roadrunner M use twin-jet propulsion to easily catch and destroy high-speed threats. But giving a human a faster interceptor doesn't solve the latency issue. When both the attacker and defender travel at high subsonic speeds, the cognitive load causes manual pilot error rates to spike. The delay is fatal when operators have to watch an isolated radar screen and manually call out coordinates over a radio to a drone pilot. To fix this, modern air defense relies on a software-defined kill chain. Hardware is no longer the primary arms race. Drone defense is now an algorithmic loop consisting of 3 strict phases: understand, decide, and act. The understand phase starts by making sense of a highly chaotic airspace. Field operators deploy a variety of radars, optics, and acoustic sensors, all feeding raw, uncoordinated data into the network. That raw data is full of clutter. Radars constantly flag commercial flights, weather anomalies, and flocks of birds. To solve this, a software layer called sensor fusion ingests the feeds from thousands of disparate sources across the battlespace simultaneously. Machine learning algorithms process this data autonomously, stripping away the environmental noise and matching signatures to known hostile profiles. The result is an intelligent, common operating picture. The human operator is shielded from the raw noise and only sees confirmed, trackable targets. Once the network understands the threat, it moves to the decide phase, calculating exactly how to execute the kill. This diagram maps out intercept geometry. If an interceptor attempts a head-on collision against a target flying 180 kilometers per hour, the combined closing speed reaches 360 kilometers per hour, halving the reaction time and leaving almost zero margin for error. If the software plots a tail chase intercept instead, it drops the relative closing speed to near zero, opening a wide window for terminal course corrections. Deep learning models run these vector calculations continuously, projecting thousands of flight paths and geometries in the background. The models also calculate the acceptable level of risk, mapping out where debris will fall to ensure civilians and infrastructure stay safe. The system does not ask the human to do this math. It filters the variables and presents a single optimal strike recommendation. The operator's job transitions from manually steering an aircraft and calculating geometry to reviewing high-value intelligence and authorizing the launch. The moment an operator clicks Authorize, the software initiates the Act phase, converting human intent into discrete machine-to-machine tasking across the network. The network selects the exact effector. Overpopulated infrastructure, it can deploy a non-kinetic drone to capture the target in a tethered net. For kinetic strikes, the ground network guides the interceptor to the target area, then hands control over to the drone's onboard edge compute. In contested airspace, attackers will aggressively jam standard GPS signals. The interceptor compensates by using visual inertial odometry, mapping the physical terrain below to navigate without satellites. In the final seconds of the pursuit, autonomous computer vision takes complete control. Pixel lock algorithms adjust to the target's evasive maneuvers in real time to secure a physical impact. By handing the terminal homing phase over to edge compute, the system eliminates human latency, automating 95% of the interception cycle. This software architecture solves the critical economic problem of attrition warfare. Currently, attackers send out drones costing $40,000, forcing defenders to exhaust surface-to-air missiles that cost millions. Low-cost, software-guided interceptors flip that math, ensuring that destroying a threat costs a fraction of the threat itself. The software also commands reusability. If the network identifies the target as a false alarm, it aborts the mission and recalls the drone. The interceptor returns to base and lands safely, ready to be refueled. The cost of engaging a false alarm drops to near zero. Because the munitions aren't wasted, militaries can launch massive defensive swarms preemptively, expanding their magazine depth without draining defense budgets. The scale of these drone attacks prompted the Pentagon to establish Joint Interagency Task Force 401. JATF 401 mandates a departure from isolated, proprietary defense hardware, pushing instead for a standardized, interoperable software marketplace. A high-value asset, like a Navy destroyer, relies on a massive array of diverse sensors and effectors. To survive, they all must plug into the exact same algorithmic command and control backbone. The most advanced kinetic interceptor is useless if the network cannot process radar data and assign a target fast enough. Securing airspace is no longer about building faster aircraft. It is about building the fastest software loop, proving modern air defense is an algorithmic architecture.